In the previous lecture, we talked about waves, and we mentioned sound waves in particular. This whole lesson is going to be devoted to sound waves and looking at their properties. Remember, we stated that sound waves were longitudinal waves that were made up of condensations and rarefactions, and you can see really good here how this works in terms of wavelength. On top, we have what would typically be inside a speaker that produces the sound. Vibration moving back and forth. If you've ever taken a speaker apart and actually held your hand up to a speaker, you know that inside there it moves back and forth, and that's what creates the sound wave or the pressure in the air. So you can see the molecules inside that chamber are being compressed, and then when it moves back, they're being expanded, and this creates waves that move through the air. The wavelengths are between the condensations, and you can just see how the waves move. It's a very good visual representation. Sound waves incorporate a lot of different subsets to them. We got sound and hearing, musical instruments, hearing, and down through all of that. We're going to talk about a lot of these different terms, mention them briefly at some point, almost all of them, so pay attention. Sound waves require a medium for transmission. What that means is that in outer space, where the molecules are so very far apart that we consider it to be a vacuum is something with no particles in it, you can't hear sound. So when you're in space, if you were able to take your helmet off, which you can't because you couldn't breathe, but if you could take it off, it would be completely silent. You cannot hear sound in a vacuum. You have to have a medium to move the sound through. So just looking at our basic three phases of matter here, gas, liquid, solid. Solid is going to move the fastest because the particles are already close together. So we looked on the last slide and saw how the sound particles collide with each other and they move down through the row. You can see in a solid the particles are very close together. We know that in a solid all the particles are combined, right? They're intermolecular forces holding them together like springs. So once you excite one molecule, it quickly moves to the next molecule, and that allows sound to move faster through a solid. If you remember the movie The Lion King, you remember the little baby lion Simba. He puts his ear to the ground and he hears the stampede coming before he can actually hear the animals in the air. That's because the sound waves are moving through the ground faster than they're moving through the air. You can look over there at gas. The molecules are further apart, so there's less collision between the molecules, so the sound doesn't get from point A to point B quite as fast. And then a liquid would be in the middle. If you ever talked to somebody underneath the water, you know your voice sounds funny, and that's based on the moving through the thing. Obviously, the temperature gets higher. As the temperature gets higher, the molecules have more kinetic energy. That means they're having more collisions. The collisions are happening more often. Sound is going to move faster. Interaction strength, that was what we were talking about with the molecules being together. And then the inertia of the molecules. The bigger molecules are going to move slower. Sound's going to move slower through a bigger molecule because it takes more energy to move that molecule. Whereas a lighter molecule like helium or hydrogen, it's going to move much quicker because those molecules are much lighter. In air, at room temperature, which is 20 degrees Celsius, or essentially 68 degrees Fahrenheit, normal room temperature, sound moves at 343 meters per second. That's about 760 miles per hour, which is pretty fast. Considering people have ridden a motorcycle that fast, I mean, that's pretty crazy, but 343 meters per second. So just to mentally visualize it, that's about 4 football fields long in 1 second. That's how long it takes sound to move. The greater kinetic energy, the faster it's transmitted. And if you look at a plane down below, stopped plane is sending out sound in all directions. Subsonic means the plane is moving slower than the sound waves. If the plane is moving at the speed of sound, the waves and the sound waves are exactly the same. And then supersonic, that's breaking the sound barrier. The plane is moving faster than the wave it's creating. So if it's going from point A to point B, the plane is already at point B before it has sent out the sound wave. So this is called breaking the sound barrier. Mach 1, that's what we call the speed of sound, is Mach 1. So the space shuttle in our atmosphere moves like Mach 9. The space shuttle, when they used to run it, that's pretty fast. So It's very, very fast, the speed of sound. When we hear sound, we call that pitch. Pitch is the frequency of a sound wave. You can see the two kangaroos hopping there on the right. The kangaroo on the top is hopping at a higher frequency, so we would say if we were listening to that wave, it would have a higher pitch. Whereas the kangaroo on the bottom is hopping at a slower frequency, and it would have a lower pitch. So humans can hear between 20 to 20,000 hertz. That's our normal range of hearing. Ultrasound or ultrasonic waves are greater than 20,000 hertz. We use ultrasonic frequencies when we're looking in a woman's womb at a baby, right? An ultrasound of the baby, and we can produce an image based on the waves that it gets back. It sends a wave in, it comes back at a different frequency, and from that frequency shift, they can produce an image. Dogs can hear ultrasonic frequencies. If you ever heard a dog whistle, maybe you've seen the movie Teen Wolf, they blow the dog whistle, right? Dogs can hear that high frequency noise that we can't hear. Bats use their echolocation. They use ultrasound they send out a signal, it hits something, it comes back at them at a new frequency, and they can tell how far away it is. Dolphins, all of those things. If you've ever had an injury and you've had an ultrasound treatment, they put the gel on your injury and they put that wand on it, and it doesn't feel like it's doing much, but what's happening is it's sending sound waves into your injury, and it goes into that scar tissue, and it breaks the scar tissue up, and it helps with the healing. It's like a deep tissue massage. And then maybe an echocardiogram, same thing. They send an ultrasound in to look at your heart, and they produce an image, and you can see what's happening with your heart. On the opposite end of the spectrum is infrasonic. Infrasonic are below 20 hertz. Elephants can communicate about 3 miles apart using infrasonic frequencies, whales, things like that. Underneath the ocean, we have a bunch of cables running between America and England, let's just say. Those cables send out these infrasonic and ultrasonic frequencies, and it disrupts the communication of some of the sea animals. So that's one way how humans are interrupting or hurting wildlife, just in terms of infrasonic and ultrasonic sounds that we can't even hear. Loudness is basically the amplitude of the sound, where pitch is the frequency, amplitude is the loudness. Our ears are really good judges of pitch. You can train your ear to have perfect pitch. If you listen to enough music, or if you play a musical instrument, you can learn the different notes, A, B, C, D, whatever the notes are. You can learn those notes because our ears can be trained to hear pitch. Our ears are really bad judges of loudness. Loudness is measured in decibels. Loudness would be on your TV when you turn your TV up, right? If you have it on level 10 or level 50 or whatever it is, our ears are really a bad judge of loudness. If you go into a nursing home, all of the people in the nursing home, you walk past their door, the TV's on level 90 and they're in there sleeping, because over time your ears get worn down. Inside your ears you have these little cells, they're like little hairs that pick up the sound, and over time those cells deteriorate, so you don't pick up the sound quite as well. If you've ever been to a loud rock concert and you've left that concert and your ears are ringing, and you woke up the next morning and your ears are ringing, well, that's the sound of those cells dying. So as you get older, you become desensitized to loudness. Just like in the nighttime, if you're out with your friends or at a party or at a bar or a club or something, and you get home and you wake up the next morning, you get in your car and you turn it on and the music's blaring, but the night before you didn't even realize it, because throughout the day your ears get desensitized to loudness. And then when you wake up and everything is all calm, you go back out to your car and your ears have settled down and it seems super loud. Kind of like when you're watching TV during the day, you have it on level 40, but if you wake up in the middle of the night and watch TV, you can watch it on level 5, because this loudness, our ears again are a very bad judge of it. That would be, the loudness is related to the amplitude of the sound wave. It's pronounced timbre, is the quality of sound. Timbre is why each individual voice or each individual instrument or whatever, everything sounds different, but it plays the same note. So if I'm playing like a C on my violin, the violin's C, the frequency of the C, the C means what frequency it's vibrating at. So the C from the violin vibrates at the same frequency as the C from my voice, but they sound completely different, because they have things called harmonics and overtones that change the timbre of the frequency. Although it's the same frequency, it sounds different. So everything sounds different, or the individual characteristics of that instrument are based on the harmonics associated with it, even though they're broadcast or put out with the same pitch. A couple other things we want to look at is boundary effects of waves, right? Sound waves in particular. We're going to look at these again when we look at light. But waves can reflect, refract, or absorb. Those are your three main wave characteristics. So when we're talking about sound, we really want to talk about reflection of sound. So the reflection is when you bounce off a boundary. So sound wave hits a boundary and it bounces off the boundary. When a sound wave bounces off a boundary, we call that an echo. An echo is you send out a sound wave, it hits something, it comes back to you. That's an echo. We can distinguish this if it's greater than 0.1 seconds. And then the other term we want to look at is reverberation. This is when you mix original and reflected sounds. This would be a musical thing that you would do too. If you play the electric guitar, you have a reverb pedal. All those different things that allow you to mix up the sounds. The final thing we're going to look at here is the reflection of sound. We call that sonar. So sonar is the sending out of a sound wave. It hits something, it comes back to you at a different frequency that it was sent out, and you can tell how far away something is. So sonar is that idea. Radar is a microwave that gets sent out, or any electromagnetic wave. It could be technically called radar, but sonar is the reflection of a sound wave that comes back at a different frequency than it was sent out, and you can determine distance and speed and things like that from sonar. We would use sonar when we locate submarines, or bats use sonar, or fish finders. All of those sorts of different things use sonar.